Okay, I will start the session now.
Yeah, sure, sir.
Okay. Hello, everybody. This is Biju or Mohan. I am heading Department of Information Technology, National Institute of Technology, Karnataka. I am talking about few statistical models that could be used for vulnerability analysis. This is the agenda of our talk actually. That is, I will explain you what is vulnerability analysis here, and a case study is also been kept as a part of this presentation. That is performance degradation analysis, and another case study is resource forecasting with ARIMA model. At the end, I will show certain. At the end, I will show. I will show a resource forecasting with the ARIMA model. Sorry for the disturbance. So, what do you mean by vulnerability analysis? So, software vulnerability analysis plays a critical role in prevention and mitigation of software security attacks. Here, vulnerability can cause due to the natural aging of software, as well as maybe due to certain attacks also. The accumulation of errors or due to excess resource consumption also, it can the system may fail or hack. Here are what do you mean by a software aging actually, that we have to explain. And that software aging means the progressive performance degradation of long-running servers, which may lead to system crash or undesirable hacks. And this phenomenon is referred to as software aging. This could be due to the memory leakage. Actually, as you know, memory leakage can happen due to a fault made by a software programmer. For example, if we forget to release a certain amount of memory, this leakage will become vulnerable for the system. See, for example, a 10 KB of memory space is not been released by him. Over a period of time, if 10 times the same function is being called, so 10 into 10K will be sort of 100K will be unreleased actually. This could be one example which I could cite here. So the performance degradation can be due to this kind of aging related bugs. As I told you earlier, it could be due to the fault which is made by a programmer. Otherwise, there could be a malicious software which would be running in the system, or a kind of denial of service attack going on in the system. These are major causes which may affect the performance degradation. In this particular session, we will be talking only about aging related bugs that may cause due to resource shrinkage. Resource shrinkage means the computer resources. Computer resources could be free available physical memory, its CPU time, or it could be its bandwidth, or maybe its storage area, or whatever it is. Actually, that the computer resources only we will be referring to here. So let us look into the anatomy of failure. As you see, this is a chain of things happening here. This is a chain of error, how error is propagating through the system actually. A fault which may cause due to the programmer, which may activate a kind of error, and this error propagates through the system and cause the system to failure. The failure here means, see, the system could not be able to deliver the internet service which is meant for actually. For example, if a file system is meant for giving or storing the files, that particular service could not be able to deliver by it. In the case of a web server or a software service which is running with certain non-functional requirements associated with it. So, for example, the response time associated with a web service. Maybe it has a response time of 3 milliseconds or something, which could not be able to deliver in this particular non-functional requirement, or it is generally called as non-functional requirements in software engineering. And it may lead to a fault also later. Later, this response time will increase, and after a point of time, the system will not deliver any kind of service to the user. This is sometimes similar to that what we see in chain of responsibility in certain software patterns, where as you have seen in exception handling and all the runtime errors which is occurring, it is a kind of chain of responsibility. If that is not being properly handled, this failure will come out. So this is a state transition diagram of a system, and this diagram is to explain you that a system starts with S0, that is when the system is in healthy state, and after a period of time it moves to SP, that it moves from S0 to SP, that is a failure probable state, and it could go to a failure state if it is unattended. If you have any rejuvenation mechanism to handle it, it could go to the state SR and follow the path S0. Again, it will come back to a healthy state. This is the state transition diagram of a system. So what is the point of talking this actually? That is what I have to explain you. The downtime and revenue loss of the rejuvenation path, that is S0, SP, SR, S0, is much lesser than the failure path, that is S0, SP, SR, S0. So a system administrator would like to do a rejuvenation mechanism rather than let the system to make a failure and comes back to the original state. And in order to identify why I have shown you this particular state diagram is, here one research problem is there. That research problem is this: when a system reaches the failure probable state, if you could able to predict that this is in failure probable state, then we could apply a rejuvenation mechanism on it, and we can reboot back it to, or we can rejuvenate it back to a healthy state S0. If a failure probable prediction state is not present in the system, then it will be difficult for the system administrator to predict that, and the system will obviously go to a failure state, and the time taken from a failure state to that means there will be some revenue loss also associated with that. So it will be and that downtime and revenue loss for the rejuvenation path will be much lesser than that of the failure path. So in order to study this particular the model, we have different mechanism in place. Actually, there is a model-based mechanism, measurement-based techniques are there, and certain hybrid techniques are also there. Actually. So here I have given a table of model-based techniques, measurement-based techniques, and hybrid techniques, which is used to analyze this whether system has moved to a failure probable state, or study the performance degradation of a particular system. So first we will go through what do you mean by model-based techniques. When I say model-based techniques, it is primarily depend upon mathematical models, which is used to analyze the system. The beauty of this model-based techniques is it could be applied at any stage of the product life cycle. But in the case of measurement-based techniques, that is, we measure the actual system, and from the measurement of the actual, certain metrics will be measured, and the measurement of the actual system should happen using certain. We have to design certain experiments, and we have to collect the metrics from the system, and this could be possible only when the system is in place, or a prototype of the system is in place. So that is why it is called post prototype. And hybrid techniques is a mixture of these two, actually. That is model-based techniques or measurement-based techniques. And another technique is also there, which has not been depicted here, actually. That is simulation-based techniques. Simulation-based techniques also can be applied at any stage of the life cycle, but only thing is the simulation environment should be there in place. And let us see what are the other points which is discussed in this table, actually. That is time required. Time required to do a model-based techniques is very small if the person who is doing the model-based techniques is good at doing that. That is, he should know the mathematical models which could be applied on this particular system. And the measurement-based techniques generally depends upon the experimentation time. The experimentation time depends upon what kind of system you are having. Actually, some systems can be meant for running for longer period of time. Some system is meant for running for shorter period of time. Example is a washing machine and a server. A visualization server is supposed to run for longer period of time. Washing machine is supposed to. That is what I mean to say. And in the case of hybrid also, the experimentation time is large. Generally, if you are looking at the servers alone, the experimentation time will be generally large. Maybe it will be 500 hours or 600 hours. The experimentation, then only we can study the vulnerability of the software components which is we are planning to run on this particular server. And generally, the model-based techniques require analysts to do the model-based techniques. In measurement-based techniques and hybrid-based techniques, you need the instrumentation. That means that I told you that is a post prototype. So a kind of prototype is required for doing that. The accuracy for model-based techniques is likely to be low because we are not testing on the prototype or on the real systems. Generally, measurement-based techniques, if the experiment and the instruments to carry out the measurement of the measures which collect from the system is good, then the accuracy is very high. And hybrid techniques also, accuracy may be high. Actually, it depends upon what kind of hybrid techniques you generally apply. The cost associated with these types of techniques is, in the case of model-based techniques, the cost is very low. It requires a pen and pencil to carry out these model-based techniques. And in the case of measurement-based techniques, the cost associated with that is very high, because either the prototype of the system should be there, or the actual system also, or the actual system should be there. In the case of hybrid techniques, it varies actually whether you are giving more. If it is both, it's a combination of model plus measurement. It will be very high. If you are laying much on the model-based techniques and less on the measurement-based techniques, it may be slightly lower than that of the measurement-based techniques. The scalability of the results what we obtain from this kind of experiments, that will be very low in the case of model-based techniques, and measurement-based techniques, it will be high. Actually, you can test it at both levels, whether the system is scalable or not. And in hybrid-based techniques, it varies actually. Model-based techniques is very easy to implement, and measurement-based techniques, its difficulty is medium. We have the real system, we don't have to go for the prototype and all. And hybrid-based techniques, it has to implement both. Actually, it will be slightly difficult than the other two. So we will come to our first case study. How will we analyze the performance degradation in a real system? As I told you earlier, we had to first design an experiment, and from the experiment we have to collect the data, and we should go for the vulnerability analysis of that. And here what I have used is a VMware bare metal hypervisor for doing this kind of tests actually, and I have given certain workload for this bare metal hypervisor, and the resource usage of this bare metal hypervisor has been collected over a period of technique, and linear regression modeling is applied, and hypothesis testing is also being done on that. And while designing the experiment, just as you know, actually servers are meant to run for longer period of time. We have used the accelerated life testing mechanisms to do that actually. What I mean by accelerated life testing is, just because servers are meant to run for a longer period of time, what we want to test, so we will introduce a certain kind of vulnerabilities to it deliberately. It's not accidentally, it is deliberately. We will create some memory leaks into the system, and we will analyze the resource usage data for such kind of experiments, and we will do a linear regression modeling and a hypothesis testing on top of that. So there are two types of hypervisor which is available. One is hosted hypervisor, and the second one is bare metal hypervisor. Hosted hypervisor means on top of the host OS only the hypervisor is running, and VMs will be deployed on top of virtual machines will be deployed on top of this hypervisor. Example is VirtualBox is an example of hosted hypervisor, and the bare metal hypervisor is one where the hypervisor runs straight on the hardware, and VM should be running on top of this hypervisor. In these experiments, we have used a bare metal hypervisor which runs directly on top of the hardware is being used there. So this is the typical setup for experiment, and the machine which we have used for testing at the server is the hardware is HP Client ML350 G6 machine. And on top of that, I have installed, this experiment has been conducted a little long back. This is a paper published by me during 2013. So the software versions which I have used is slightly older. And the SP planned ML350 G6 machine is used for testing the hypervisor. And the hypervisor, which or the VMM, the virtual machine monitor, which is used here is VMware ESXi 5.00, and certain some 20 clients have been used to load this thing. Here the clients is accessing certain pages which is there in the web server, which is Tomcat, and which is running on top of an Ubuntu operating system. And we have created certain pages in each of these VMs, and we have used a tool called HTTP for accessing these pages, and from the VMware ESXi 5.00, we will be monitoring the system variables. When I am telling this, monitoring the system variables, we will be collecting the system variables using a command called ESXstop, which is running every half an hour. It will collect the system variables. Which system variables we have collected, I will explain later in this presentation. And this experiment is used to analyze the vulnerability of the VMM, that is the hypervisor, which is running on top of our server. So the metrics collected are the response time of the web server, CPU usage, that response time. Rest two things we are not using in the current presentation, that is reply rate and timeout rate. And the CPU usage, disk I/O usage, and the swap space usage, and number of interrupts called, and number of context switches, and bandwidth usage and power usage are all collected. But here we are using the CPU usage, and the one more thing which I left out is the available free physical memory, which also we are using in order to analyze the performance of the server actually. And there are 4 memory reclamation techniques which is running on this VMware ESXi 5.0. And that is transparent page sharing memory, ballooning, hypervisor strapping, and memory compression. What do you mean by transparent page sharing? That is because if 2 of the images of or 2 pages in the memory is same, and they may do a hash checking or something to analyze that whether the pages which is available in the memory. This memory reclamation technique is used to enhance the resource usage. Memory is one of the computer resources, as you know, and transparent page sharing checks whether the similar copies of the pages are available in the VMM. If the similar pages of the pages are available in the virtual machine monitor or the hypervisor, one copy is left there and the rest of the copies is being removed. If any write is there, then another copy will be brought back to the memory. This is the technique behind transparent page sharing. While doing these experiments, we have switched on the transparent page sharing in order to make the resource utilization very high. The second technique is ballooning. This is being done inside the virtual machine. A driver is there. If the particular virtual machine is not using much of these resources, then what will if this or the virtual machine monitor will inflate its usage by with the help of this driver, and the the memory allocated for that virtual machine can be used for some other purpose. This is the technique behind ballooning. And hypervisor swapping is another technique, which is slightly costlier in terms of computational footprint. And what hypervisor swapping means is uh, a virtual machine itself could be swapped to the memory when the virtual machine, which the entire system thinks that more memory is required for some other operation. Another one is memory compression. In the unused, the least used memory pages will be compressed and kept, so that the available memory space will be higher. These are the things which we could explain during this thing. Most of the data which is occurring in this thing is in the form of time series. So what I mean by time series, I have to explain. Time series is a series of data points indexed in time order. This is what Wikipedia says. And most commonly, a time series is a sequence that is taken at successive, equally spaced points in time. So this is a discrete data set, and this will be collected over a period of time. In this case, most of our data set, for example, whether it is free available physical memory, or percentage of CPU utilization, or power usage, or whatever it is, all are a time series which we collect at some point of time, and this is equally spaced also. So let us look at the average response time. Average response time of our web server. We can see that average response time of our server is increasing, and this is due to that there is some sort of, let us see whether it is used due to the resource shrinkage. It might be due to the resource shrinkage in time actually, and the errors which is induced to the system is in accelerated mode. As I told you earlier, the server here the server is a device which is supposed to run for longer period of time, and in order to as the experimentation time in this case is very high, we have to deliberately put certain amount of errors into it, so that the failure will be faster. So in this case, the experiment is designed such that a certain amount of memory leak is deliberately introduced into the servers in order to make the average response time, or make the server degrade faster, or in terms of performance, degrade faster in terms of performance. In here, we could see that the average response time of the web server increases over a period of time, and you can see that the time is in hours, and by 150 hours, that you can see that the average response time has gone to more than 400 milliseconds. That is very high. And the available memory in bytes, megabytes, plotted against time in hours. The free available memory in megabytes, which is plotted against time in hours, as you know that the free available memory tends to shrink over a period of time, that is time in hours. And as you know, actually this is deliberately done. We have introduced a certain amount of memory leaks to the system, and the time, as you know, actually that memory is shrinking over a period of time, and we could see that there is a trend in it. And for that, we are using a linear regression model, and we will use a we will use hypothesis testing to check whether this has significance. This is the percentage CPU utilization, which is plotted against time in hours. As you know, actually, this percentage CPU utilization is increasing over a period of time, and it is reaching almost 100. And this shows that the computer has reached a stage called thrashing. And power usage in watts against time. This is also being plotted here, actually. And power usage in watts is increasing over a period of time, and this will reach to almost a peak when we reach the time of time, like as the experiment reaches 150 hours of time. And how linear regression and hypothesis testing can be used in order to test the significance of this performance degradation. That is what next few slides we will check. And linear regression is a very simple regression model which is used to predict what is y after a period for a particular value of x. It is in the form of the equation of a line, that is y is equal to mx plus c. And here you know that y is equal to beta 0 plus beta 1 x plus epsilon, where y is the dependent or response variable and x is the independent variable, where beta 0 and beta 1 are generally called or usually called regression coefficient, and epsilon is the error associated with the prediction. Beta and beta 1 can be estimated in different ways. If you are estimating it using a linear square estimators, we have to, in order to minimize the error, we have to subtract what is predicted and what is observed. That is y minus y cap. And if you partially differentiate this one, that is y minus y cap with respect to beta 0 and beta 1, you may get two equations. By solving these two equations, you will get the value of beta 0 1 and beta 0 and beta 1. And which is been given here. Beta 0 is y bar, that is the average value of the total y's of the of the data set, and beta 1 cap by into x bar, actually, where beta 1 can be obtained from x and y values as shown in the equation 3. So once we obtain the value of beta cap and beta 1, the fitted symbol linear model can be expressed as y cap, that is the predicted value using this model, and with respect to x, with respect to that of x.
Hello, sir. Okay, okay, again sharing. Okay.
Now, whether I stop sharing and whether I have to start again?
Yeah, sir, please do it, sir.
Okay.
Participant, wait for a minute actually. There's a connection problem. Sir will join in a minute, he will join. Please wait.
Now it is visible?
Yes, sir, it's visible, sir. Please continue, sir.
So participants, whether if they have any questions, they can stop me and ask that, because I could not able to know whether you are following me or not.
Sir, here the problem is, since the recording session is going on, and they suggested after the session they will ask you a question, sir.
Okay, fine.
Okay. So from the previous slide you proceed, sir. The largely regression you explained, sir. Previous slide.
Yes, one second. Here?
Yes, sir. Yes. After this slide, sir. After this slide. Next slide.
Okay.
After this, we couldn't hear you, sir.
Okay.
Yeah, please.
Okay, fine. And this linear regression model, which is in the form of y is equal to beta 0 plus beta 1x plus epsilon, where this is in the form of a line actually. And as I told you, how to identify, how to get beta 0 and beta 1. Here it has been, the equation is, we have estimated it using least square estimators. Least square estimators depend upon the squared errors, actually, squared errors. And the squared errors is differentiated with, partially differentiated with beta 0 and beta 1. And we get two equations from there. We solve that and we'll get beta 0 cap and beta 1 cap. And this y cap is we'll get y cap as beta 0 cap plus beta 1 cap xi, where xi is the, in this case it is time actually, and y is what you want to predict. So in the case after fitting the model, we would like to know what is the whether the model is good to fit that data set or not. And here one measure is there are two now. Here we are using a hypothesis testing to know that whether the fit is good or bad. And another measure which comes when you fit the data set in R and Python, you can easily fit that with one line of code. And if that is the coefficient of determination. By looking at the coefficient of determination, you can easily tell that whether the fit is good or bad. The coefficient of determination, or R squared, gives the goodness of fit of the model of a simple linear regression model. Generally, it ranges from 0 to 1. If R squared is 1, then we can tell that the regression is good. That means the fit is good actually. But there are certain riders where we have to check for the homoscedasticity and heteroscedasticity. That is beyond the scope of this talk. And the coefficient of determination can be obtained by the ratio of sum of squared of errors of due to regression and divided by total sum of squared of errors actually. What you mean by total sum of squared of errors is the observed value minus the average of the observed values. That is y minus y bar, the whole squared. That will be the sum of total, the sum of squared of the total error associated with that. And sum of squared due to regression is y cap I minus y bar, the whole square. That is added over a period of time. The square added over a period of time. And sum of squared of residuals is the actual residuals what is obtained by subtracting yi minus observed, the predicted value y cap. And yi, y bar and y cap are observed, average and predicted values of the response variable y. So we would like to test the significance of regression. There is one way to test the significance of regression. that is hypothesis testing. Here we will state one hypothesis that, as you know, actually, as I told you earlier, the linear regression is in the form of y is equal to mx plus e. That is the same equation which is used to form a straight line. Here it is y is equal to beta cap plus beta 1x1 xi plus sigma. And if the beta cap is equal to 0, like beta 1 is equal to 0, that means there is no slope for the line. That means the straight line, this will be a straight line which is parallel to that of the x-axis. Then there is another way to test this actually, that is by looking at the Pearson's coefficient of the particular data set with respect to the time the x with y actually. If the Pearson coefficient is significantly nearer to 1, then we can say that this has a significant impact on this. This is the other way of doing it actually, by testing the significance of regression using a hypothesis testing. In this, we will state two statements, that is null hypothesis and an alternative hypothesis. Here 0 is represented as the null hypothesis, which says that beta 1 is equal to 0. That means there is no significance between. That means the y is not moving just because of the that of x actually. That is what it means actually. That means there is no significant or there is no correlation between y and x in this case. That is beta 1 is equal to 0. The other alternative hypothesis is beta 1 not equal to 0. And if we reject beta 1 is equal to 0, that means there is a significant impact between y and x. There are three ways of testing the significance of this thing and this particular hypothesis. That is t-test, analysis of variation, and confidence interval of beta 1. But here we will use only one to see how the significance of the regression. How will we do that? The hypothesis, that is a 0. Beta 1 is equal to 0. That means to test that whether we don't have whether there is no relationship exists between y and x, we have to calculate T0, that is beta 1 cap divided by standard error associated with beta 1 cap. That is standard error associated with beta 1 cap is obtained by sum of residual square of errors divided by S of SXX. That means, and about the equation is being given, a sum of square of residuals is being obtained by y cap minus y, that is the predicted value of the y minus the observed value of yi, the whole square, sum of that actually. And Sx it's a straightforward equation, that is xi minus x bar the whole square. The null hypothesis, that is x0, beta 1 is equal to 0. That means there is no significant relationship between y and x. This will be rejected if the absolute value of t0 is greater than t alpha by 2 comma n minus 1, n minus 2. Here n is the observation and alpha is the level of significance. Normally it will be taken as 0.5. So we will test the model with 95% of significant level. As you know, actually, in the results obtained here is not being shown. The reason it is the part of one paper, and basically the idea is to tell you that A linear regression line and hypothesis testing can be used in order to know whether the performance degradation happens in a server or not, actually. And here it is clear that the average response time is increasing and the memory is shrinking and the percentage of CPU utilization is increasing. Even power usage is also increasing with respect to time, which shows that the average that the web server is degrading with respect to its performance over a period of time, with the memory shrinkage and the percentage of CPU utilization and the power usage is increasing over a period of time. And this could, from this we could tell that the system is going through a performance degradation, and maybe it is due to aging related error propagation. So we will go to the next case study, that is case study 2. I think this is the this is the last case study where a time series model is being used for forecasting the resources. As I told you in the state transition diagram, there are 4 states for that state transition diagram which I have shown earlier. And as I told you earlier, when the system is in healthy state, over a period of time, it will move to the state called a failure probable stage, and from there it could go to either to a failure state or it could go to a state called SR, that is the rejuvenation state. And if it follows a rejuvenation path to S0, that is the earlier model, which is a state transition model, which we have shown you earlier, that the time, the revenue loss for that will be lesser actually. So in order to predict that the system is at the failure probable stage, we may have to forecast the resources of the system using certain models. Here the model used is ARIMA, that is autoregressive integrated moving average model, and how we have to go ahead with this thing we'll see. As said earlier, we need to design one experiment, and as the server is supposed to run for a longer period of time, we have to induce the errors in the server deliberately rather than we have to wait till it goes for a natural death. And this data is collected and is modeled using ARIMA, and we will see whether we could forecast the resource usage using ARIMA, and whether ARIMA is a good model for doing that. And this is done by doing a residual analysis on these results. So what is ARIMA actually? ARIMA is a autoregressive moving average integrated model, and it has 3 parts actually. One is the autoregressive part, the moving average part, and the integrated part. Integrated part is basically how many times you have difference this type series, and as I told you earlier, why this model is apt for looking at or used for predicting the resources. Most of the resources what we collected is in the form of time series, so it is against time. So it will be, this model is apt for doing that. That is what our initial assumption is. So we'll see what will happen when we go ahead. So the first step involved in fitting the model with ARIMA is plot the data to find the patterns and irregularities. Sorry for there is one mistake there. Irregularities. If we required cleanup the outliers and missing values, we haven't done that. If you want to take the logarithm, you can convert this thing to a log of that y. And examine trends, seasonality if present, and remove the trends and seasonality. Just because in order to make the series stationary, we may have to remove the trends and seasonality in the data set. In order to know whether the data set is stationary or not, we have augmented decay polar test. It is a unit root test to check whether a data set is stationary or not. If the data is non-stationary, then we have to make it stationary by differencing the time series. And we could use autocorrelation function and partial autocorrelation plots to determine whether the order of the AR and MA terms which is present in the ARIMA model, and you can fit the ARIMA model. This is the steps which is followed in this procedure. Generally this is called Box-Jenkins model in order to fit the ARIMA model. And here the research part is by looking at ACF and PCF, you should get only the clues of how many AR and MA terms is available in the ARIMA model. Still, that part is not clear from the literature. Actually, that means there is some research gap there. So, if someone wishes to look at that research gap, that again will be give good research results. So here a few time series is being depicted actually, and this is being taken from one website, and I think these are all stock prices and some product thing which has been shown here. You can think that this is typically a resource usage data also. And we can see in the plot A, there is a significant trend in the data which is moving upwards. That means when I say that time series is stationary in nature, first two moments of this data should be constant actually. That means the mean and variance of the data should be same throughout the different periods of time. And as you know, actually in the plot number A, there is a significant trend upwards. The B, if you see, it is a stationary time series, but only thing is after 150, there will be a significant spike in the data, which may cause some issues actually. Otherwise, the data is stationary in nature. And you can see the figure number 4. Here the mean of the data, if you see the mean of the cross-section of the data, which varies across the period of time. And even variance also significantly changes. And in D also that this is the same problem. And in the E, there is a significant downtrend. And in F also there is a significant variation in the mean and variance. That is stationary in nature, and I, if you see, there is a significant trend, and H, there is a seasonality in the data. You put that beer sales is seasonal in nature, and this is in order to explain you what you mean by seasonal stationary in nature, and what the assumption is time series is thought as a collection of random variables. It's a collection of random variables. Each random variable has a distribution associated with that, and its mu and sigma, that is standard deviation, varies across. Assume that this is taken from a normal distribution. This mu and sigma varies significantly. Our assumption here is it comes from a same distribution, but actually it is not true in nature. What do you mean by autoregressive model? Actually, autoregressive model is a model which is used to regress its own value for getting the phi. For example, the yt is equal to c plus phi 1 yt minus 1 and phi 2 yt minus 2 etc. up to phi p yt minus 1 epsilon t, where epsilon is the white noise here. Epsilon white noise means it is come from an independent and identical distributed thing with zero mean and standard deviation 1. And as you see, actually yt can be, in the case of AR model, yt can be easily predicted using the previous values of y itself. That means, for example, if gold price can be predicted with previous values of gold price, then that model is called AR model. If you can predict the current value of a particular computer resources using the previous values or the values of the previous time periods, if you could able to predict that, then we can tell that that is in AR form or autoregressive way actually. And if the phi 1 is equal to 0, then it is equivalent to white noise. In the case of an AR1 model, that is yt is equal to phi 1 yt minus 1 plus epsilon. Then if phi 1 is equal to 0, then yt is equivalent to a white noise. If phi t is equal to 1, this is a special case, and c is equal to 0. Then it is called a random walk. It is called a random walk. That means that yt depends upon the previous value of y plus some error term associated with that. In this case, there is no drift in it. That means c is equal to 0. And if c is not equal to 0, then it is a random walk with the drift. And if phi 1 is less than 0, then it is oscillate around the mean angle. Next is MA model, and here sigma epsilon t is a white noise, and MA model gives is actually regression model on the previous noises, and that means if yt could be represented as c plus epsilon t or plus sigma theta 1 epsilon t minus 1 plus theta 2 epsilon t minus 2 up to theta q epsilon t minus q, then we can say that this particular y is can be characterized using an MAQ model. In fact, ARIMA model is the combination of AR, MA, and how many differences you are going to make. That will tell the order of I actually. This is a different experiment. Here I have plotted the free physical memory with in megabytes with respect to the time in hours. And this free physical memory is going to be predicted using ARIMA model. And as you see that this is in fact it is moving haphazard, but we could not see as it is not plotted in a very micro level actually. That's why we could not see the movement of the free physical memory. And as you know, actually, at the end of the uh, 250 hours, the free physical memory is being released. As I said earlier, there are certain memory reclamation techniques which is happening inside the. That is not out there. That is what I mean to say, that it is not an outlier. This is because, as I told you earlier, there is a few memory reclamation techniques which is being there in virtual machine monitor. That is page that is TPS, transparent page sharing, hypervisor swapping, and ballooning, and the memory compression. Here at the end of the session, as I have told you that the experiment deliberately induces certain amount of memory leaks into the system. The system finally reached almost at the 250, near 250 hours actually. It's after 200 hours. It has gone to a state called SP. And from that state, that is a state we would like to predict actually. That is a state where we should know that whether this particular model is capable of predicting as the system has moved from a, a healthy state to a failure probable state. From there, it has moved to a failure state. After 200 hours, it has moved to a failure state. And if you know that as this free physical memory has shooted up at the end of the 200 hours, you can see at the end it has shooted up. That is because the hypervisor swapping has been in place, and the virtual memory, the virtual machines which is there running on top of this VMM is being swapped back to the storage, or swapped back to the storage space in order to release more free physical memory. And this is very clear from, I forgot to put the swap read write plots also. From the swap read write plots, it is very clear that at the end that swap read write rate is very high, which tells you that that system has reached a failure state. So in order to know what is the trend, how many AR and MA terms is there, we have to plot autocorrelation function plot for this particular time series. So autocorrelation for K lag will be given by this formula, which is taken from some textbooks, and here YT is the Y value, observed value at time t, and Y bar is the average Y value, and YTK minus 1 is at time t minus k time, and Y bar is again the average of it. And this is similar to that of a correlation formula itself. And by using this, we have plotted the ACF plot for that particular time series, that is free available memory. And we found that there is a significant lag. How will you know that all the lags are significant? There is a blue line which is there. It shows the whether the memory values are significant or not. And we can see that almost all values are significant in nature, and we could not, with this model, we could not able to predict, by using this kind of data, we could not able to predict using the ARIMA model. As in the PACF plot also, that is partial autocorrelation function plot, we could not trace anything from there also. For that reason, we have differenced the series once, and we have again plotted the ACF, that is autocorrelation function of the differenced series, and found that there is no significant lines above that blue line actually. So this is the This is the ACF plot of the difference series. How will you know? What do you mean by difference series mean? Yt will be subtracted from yt minus 1, like that we will get a difference series. And this ACF of this difference series is being plotted here actually. And we can see that there is no significant lines for this ACF, that is autocorrelation function of the difference series. And from this it is very clear that we could not able to plot or we could not able to predict with this particular model actually. And PACF of the difference series also is being shown here, and it is clear that there is no significant line for PACF plot also. So, and there are 3 criterions to check the goodness of it. That is Akake information criterion and Akake information criterion corrected and Bayesian information criterion for checking the goodness of it of these models actually. As we predicted earlier by looking at the ACF and PACF of the graphs, that this ARIMA models is not good enough to predict the resource usage of the virtualized that hypervisor. The results also shows, as we fitted and we found out the goodness of it from these models, and the goodness of this the model shows a very high value, which shows that these models are not good enough to fit or not good enough to use to predict the failure power stage or the resource usage of the virtual machine monitor or hypervisor or the hypervisor. So the results are negative, but we have learned that how to use this ARIMA model for predicting the resource usage of a virtualized virtual machine monitor or hypervisor resource usage. So let us move to residual analysis. Whether by looking at the residual analysis, we'll be able to give good clue about whether the model is good or bad. And generally a good forecasting method will produce residuals with the following properties. That is, residuals are uncorrelated. There should not be any correlation between these residuals. And if there is a correlation between these residuals, how you can do is you take the Pearson correlation coefficient of these residuals. You will know that whether there is a correlation exists between these residuals. Then there is an information left in the residuals which should not be used for computing forecast. That means if the first and foremost important thing is residuals should be uncorrelated. And the residuals should have a zero mean. You can easily calculate the mean value of the residuals by taking y cap minus yi. This will give you the residuals, or the fit dot residuals will give also in R that it will be easier to get the residual values. And in Python also it might be easier. And by looking at the mean of that residual values, you will be able to tell that whether the forecast is biased or not. And the third point is the residual should be normally distributed. It should be normally distributed with around the mean, and the residual should have a constant variance. By plotting the residual curves, we easily see that whether it has a constant variance or not. This is the plot of the residuals. We could see that a fat tails at the end of the residuals. As we predicted earlier, at the end, the system has gone for the system has moved from a normal running stage to a failure probable state, and this reflects in the residual plot also. And from this, we can easily tell that this model is good enough to predict the resource usage. And in order to there are certain ways to cope up with such kind of fat tails. So that is means that the clustered volatility at the end. Clustered volatility. This is called as clustered volatility. And in order to cope up with that, we have certain models. And if you see the normal plot of the residuals, also we can see that this is the one of the condition of the residuals, that is the residue should be normally distributed. The residue should have a constant variance. These two condition is failed here actually. That if you see the normal condyle plot of the residuals, you can see that the residuals are not normally distributed. If the residuals are normally distributed, it should be in the line, that red line. All the residuals should be in the red line. In this case, we can see that residuals is not there in the red line. And from the normal condyle plot, we can easily tell that the residuals do not follow a normal distribution. So we have to introduce one term called heteroscedasticity here. So that means when a time series is said to be heteroscedastic, if the subpopulation of the time series have different variables from others. What is the problem with heteroscedasticity is it is a major worry for regression analysts because we are trying to predict the resource usage of the VMM, that is hypervisor, that is virtual machine monitor of the hypervisor, and it can nullify many of the signals because all the tests which we may have conducted earlier will be insignificant. Even the null hypothesis or whatever test we may have done on this data set will be nullified because as we assume that modeling errors are uncorrelated and uniform. That assumption has gone wrong here, and you know that this models is not suitable for predicting the resource usage. The assumption of the linear regression model is that there is no heteroscedasticity in the main assumption when you are applying linear regression or any regression model is there is no heteroscedasticity in the model. This may violate Gauss-Markov assumption. What is the Gauss-Markov assumption? We will see. This is the Gauss-Markov assumption about the residuals, that the mean of the residuals is equal to 0 and it should have a finite variance. That means it is homoscedastic in nature, and the error terms are uncorrelated, where the epsilon I is the error term. Breaking the assumption of Gauss-Markov theorem in linear regression model now is not the best linear unbiased estimator. The blue property of the estimators may go off. That is the reason why we should follow the Gauss-Markov assumption. There is one test for heteroscedasticity is explained in next actually. It is called Goldfleck-Kohn test actually. This is used to check whether the data set is homoscedastic in nature, or it do not have the property of heteroscedasticity, or whether a presence of heteroscedasticity is present or not. Actually, that is basically this test is for. And what we have to do is rank the observation according the variables is ranked according to the ascending order, and first is then a C central observation is omitted, and we may get n minus C observation in two equal groups. What we will do is we will fit two linear regression lines in this two observation, and if the residual sum of squares of this thing does not follow is not equal to 1, then we can assume that the the data set is heteroscedastic in nature, or the homoscedasticity is not present in the nature. Basically, this is an easy test actually. What we have to do is we have to divide the data set into two and omit C central observation, and then we have to fit two regression lines in both these data sets, and we have to see that the residual sum of squares of the residual sum of squares is the ratio of the residual sum of squares is equal to 1. That means it is same. So there are two models again. If you wish to continue further, that is an autoregressive conditional heteroscedastic model and generalized autoregressive conditional heteroscedastic model. If you find that the data is having heteroscedasticity, that means after doing an ARIMA modeling, there should be a mean model for fitting the arch or gauge model. What is the first thing you have to do is you have to take the data set, you have to fit it with linear regression model or ARIMA model, and you take the residuals and do a residual analysis on this residuals and find that whether there is a heteroscedasticity present in that. There are a number of tests for heteroscedasticity. One such test we have explained earlier, and what we have to do is then if the heteroscedasticity is present, then we can fit it with. That means if it is an arch model, the variance will be dependent only on its previous error values. Actually, that means that sigma square t is dependent on time. That it depends upon the previous values of the error values. And if it is a gauge model, then the variance will be dependent upon the squared values of the error and the squared values of this previous variance. This is being explained by the equation 28 and 29. And if you wish to do, what you have to do is first you have to fit it with ARIMA or a linear regression model. Then you take the residuals of that and fit it using an arch or gauge model. And arch gauge packages are available in capital R. That is a statistical software tool which is free downloadable, and you can fit it using that. That's all I think actually. Thank you very much.
Hello, sir. Thank you, sir.
You can ask.
Yeah. For participants, if you have any questions, you can post in a question answering thing. I think sir will answer.
Do we have any questions?
Participants? So far, we haven't faced any questions so far. Okay, sir. Okay, I think no questions from participants. I think, sir.
Okay, then thank you very much.
Okay. Thank you, sir. Thank you for joining with us. Abbas, can you stop recording the session?
Yes, I'll stop recording.